So what are metal carbonyl compounds or synergic bondings? So this synergic bonding, you can see here, the synergic bonding is generally observed in metal carbonyl compounds. So what are synergic bonds? Before going with that, first we have to understand what are classical ligands and non-classical ligands. See, if there is a metal complex the atoms which, or the group of molecules or something like some elements, right? An atom, either it should be an, like, ligand will be like an ion, like anionic ligand, it will be an anionic or neutral. Okay, so which will be having a negative charge or lone pair, which will be giving the metal the electron through a coordinate bond, right? So those ligands are called as the classical ligands, that is the normal ligand, okay, which can give the lone pair of electrons or negative charge, basically lone pair of electrons only, a pair of electrons to the metal complex or metal ion. So these ligands are called as classical ligands through sigma coordinate bond. Okay, since two electrons are shared by the single ligand, it is called as coordinate bond. It's not a pure covalent bond, it is a coordinate covalent bond, correct? So these type of ligands are called as classical ligands. Now what are non-classical ligands? Non-classical ligands, for example, you already have been studied in metal, so there is a speciality in metal geometry. For example, if I am taking a metal with octahedral, normal some metal I am taking, metal in some X plus N plus oxidation state. Octahedral, if I am taking 1, 2, 3, 4, 5, if a strong field ligand came with, I am saying D6 configuration, so 1, 2, 3, 4, 5, 6, it will get paired up, you know, in the presence of a strong field ligand it will get paired up. So the geometry will be this D, later S, if it is 3D, then 3D, then 4S and 4P, outer 4P. Since in octahedral means 6 ligands will be there totally, and this each six ligand will give its lone pair of electron coordinated through this newly hybridized orbital, which will be a combination of this and this. So D2sp3. So this D2sp3 is each one is D2sp3. This is D2sp3. This one also be D2sp3. So each newly formed hybridized orbitals, this ligand will be giving its electron. So these each one is coordinate bond, right? So you can clearly see that here the metal non-bonding electron does not have any role in geometry, because its geometry is determined by this one, which is an octahedral geometry, which is purely determined by the ligand. Ligand lone pair has been determined the geometry of that particular metal complex. So you can clearly see these metals are stereochemically inactive. Means, stereo means what? Geometry or spatial arrangement. So this lone pair is not at all giving any kind of geometrical aspects or any contribution towards the geometry of that particular complex, right? So these lone pair, but in case of synergic bond, when we call it in synergic bond, so these lone pairs are non-bonding, right? So when the synergic bond is happening, we know metal has d orbital which contain electron pair. Here you see it already, which contain electron pair. So if a non-classical ligand, for example CO, C triple bond, okay, so this comes, if CO is coming, CO has vacant pi star and the bonding orbital. CO, carbon monoxide ligand, has a vacant pi star orbital. Okay, so what will happen? This lone pair, this non-bonding electrons can be given back to this anti-bonding orbital. This lone pair can be given back to anti-bonding orbital. So what happened? So this is an anti-bonding. Anti-bonding orbitals are higher in energy. You know, when pi bond split, if pi is bonding and ABMO, this is bonding and this is anti-bonding. If I am saying anti-bonding has higher energy, bonding has lower energy. So if electrons are getting filled in a higher energy means destabilized. So what will happen? The CO bond become destabilized and CO bond become weaker. So what will happen? Here metal to carbon bond strength will increase because this is getting additional pi bond character. If metal is giving the electron to this one, it is getting an additional pi bond character, and to where it is giving? To the pi star, to the anti-bonding molecular orbital. So what will happen? The bonding between C and O. Okay, so metal, carbon, C, double bond. This will become weaker. The pi bonding character in CO become weaker and metal carbon will get an additional pi bonding. So this bond strength increases, this bond strength increases and this bond strength decreases. So what will happen? This bond length, if bond strength increases, bond strength is inversely proportional to bond length, because if more strengthier, bond will be more stronger and it will be very less, right? The length will be less. So this has been bond strengthier, it becomes strengthier, so bond length has been decreases. Here bond become weaker, so bond length become increases. And now about the frequency, stretching frequency. Stretching frequency is a factor of stretching frequency of CO. Okay, what happened? When there is a high back bonding, okay, this effect, right, first of all, this effect of back bonding, metal is giving the electron pair to this one, right? So this is called as back bonding or synergic bonding. Synergic bonding. Okay, this is called the synergic bonding. So this back bonding, what will happen? High back bonding weakens CO bond, right? So when CO bond is weakened, its stretching frequency also, become less. Okay, so how to consider it? Consider like a string. Consider the CO bond is a stronger bond which considered as a string. You may be already knowing about the Hooke's law and all. Like there, if a string, just a normal string which is very tightly bounded string, you stretch it and release it. Okay, so it will vibrate in higher frequency. Whereas you took a loose bond string and you stretch it and leave it, it will vibrate in less frequency. The same thing will be happen if CO bond strength is more. If bond strength is more, it will be having high stretching frequency. But if bond strength is less, which one? CO bond length is less, its stretching frequency will be less. So that is why if metal is like giving the electron to CO pi star, the bond strength become weaker, so stretching frequency also become weaker. Okay, so when this all will happen, what is the order of like getting the stretching frequency? Synergic bonding. If metal has high electron density, high electron density, basically the negative charge should increase. Then back bonding or synergic effect also increase. Why? because if metal has high electron density, then it can easily give. So higher the charge, or not the charge, higher the negative charge on the metal, more will be the stretching frequency, more will be the synergic bonding. Now some of the examples of non-classical ligands are actually CO, Cn minus, N2, NO plus, NO. This can be act as sigma donor, means I told you metal ligand will give the electron pair through the metal through sigma bonding. So these are sigma donor, and pi acceptor means it will accept the electron to the pi star. Okay, so they are pi acceptor. And some other ligands like PH3, PF3, PCl3, PET3 and PPH3, they are again sigma donor and pi acceptor. But what is the difference between this pi acceptor and this pi acceptor? Here actually in this case, pi star anti-bonding molecular orbital will accept. Okay, but in this case pure d orbital, vacant d orbital are present to accept. Okay, here the d orbital will be free to accept the electron. Here the pi star orbital will be anti-bonding molecular orbital will be there to accept. So keep in mind that pi star, if the electrons are getting filled in pi star in higher energy orbital, then only this bond is becoming weaker. If it is in normal d orbital, it is getting additional pi bond character only, it will not get weaker. Okay, now other one is, some more examples are C2H4, pi C3H5, pi C5H5 and pi C6H6. Means these all are accepting through the all are giving through the pi itself. They are pi donor also, pi acceptor also. Means for example C6H6 I am taking, there are pi electrons to give through coordinate bond, right? There are pi electrons to give, so they are pi donor and pi acceptor. Pi acceptor means it will be accepting to the pi star, because if it is having pi bonding, it will be having its pi anti bonding also. So they are pi accepting, pi star accepting. Okay, so yes, I hope you understood about the concept. So let's do a small question. So the question is that the bond length between carbon and oxygen in CO molecule is 1.128 angstrom. Then what will be the DCO, okay, distance of CO in Fe CO. Okay, option A 1.128 angstrom, option B 1.72 angstrom, option C 1.115 angstrom, and option D 1.15 angstrom. Okay, let's solve this. See, in normal CO, the bond length between normal CO molecule is 1.1. So in normal CO molecules 1.1. What will happen here? Metal is there, metal ligand is there, so metal can back bond this one. So when back bonding is happening, then CO, it is filled to pi star of CO. So CO bond become weaker, it become weaker. So if it is becoming weaker, bond length will increase. So that increase will be but slightly increase. slight increase. It is not like it is increasing a very large. So here you can see there is no change. Here you can see a large increase. Here, okay, here again decrease, 128, 115. So it is decrease. Here you can see a slight increase is there. So answer will be this. Okay, so thank you.